Tonight, consider something strange. The sun is burning at 15 million degrees at its core. It has been burning for 4.5 billion years. And it is close enough that on a clear afternoon, it can blister your skin in under 20 minutes. And yet the space between here and there, the space the light crosses to reach you, sits at 270 degrees below zero. Colder than anything on Earth, colder than anything in the natural world you have ever touched. That is not a contradiction most people sit with for very long. But here is what makes it genuinely strange. Space is not cold because the sun is far away. The sun could be right next to you, and the void would still be almost absolute zero. Cold is not the absence of stars. Cold is what the universe is made of. Warmth is the accident. And that distinction, quiet as it sounds, changes everything about how this universe works and what it means that anything warm exists inside it at all. If you find yourself drawn to questions like this, the ones that sit just beneath the surface of things, do me a small favor and hit subscribe. It helps this channel reach more people who like to think slowly about large things. Make yourself comfortable. Let's begin. For most of human history, heat was considered a thing, not a behavior, not a property of matter in motion, but an actual substance, invisible, weightless, flowing from hot objects into cold ones the way water flows downhill. Scientists called it phlogiston in the early days, and later caloric. The idea was elegant in its simplicity. When you held your hands near a fire, caloric fluid drained from the flame into your skin. When iron cooled after being pulled from a furnace, the caloric was escaping, dissipating into the air around it. Heat was a liquid you could not see. It was a reasonable theory for its time. It explained most of what people observed. Fire transferred something to the things it touched. That something made them warm. When the warming stopped, the something had moved on. The model worked well enough that it survived for over a century, carried forward by intelligent people who had no particular reason to question it. The trouble came slowly, as it usually does. In 1798, a man named Benjamin Thompson, known later as Count Rumford, was supervising the boring of cannon barrels in a Munich arsenal. The process involved rotating a blunt drill against a cylinder of bronze for hours at a time. And what he noticed, watching this happen day after day, was that the heat produced seemed to have no limit. The longer the boring continued, the more heat emerged. If caloric were a finite fluid stored inside the metal, it should have run out. It did not. Thomson wrote about this carefully, methodically, without drama. He concluded that whatever heat was, it was not a substance. It was being produced by the motion itself, by friction, by the mechanical work of one surface moving against another. It took several more decades for the idea to settle fully into science. James Prescott Joule spent years in the mid-1800s running careful experiments, dropping weights, turning paddle wheels inside water, measuring the temperature rise with extraordinary precision. What he found again and again was that mechanical work and heat were interchangeable. A specific amount of motion produced a specific amount of warmth, every time without exception. Heat was not caloric draining from one place to another. Heat was the motion of molecules. It was what matter did when its smallest pieces moved quickly, collided frequently, vibrated in place at high speed. In simple terms, temperature is a way of describing how fast things are moving at the smallest scale you can imagine. A hot cup of tea is not full of caloric fluid. Its water molecules are moving fast, colliding against your hands, transferring some of that motion into your skin, and your nerve endings interpret that transferred motion as warmth. A cold stone is not depleted of caloric. Its molecules are moving slowly, barely vibrating, with almost no energy to transfer. When you press your hand against the stone, your faster-moving molecules transfer energy to its slower-moving ones. You feel the departure of that energy as cold. This is what heat is: motion. Specifically, the average kinetic energy of the particles inside a material. And the reason this matters enormously for everything we are going to talk about tonight is what it implies about empty space. Consider what a vacuum actually is. Not the vacuum of a household appliance, which is simply low-pressure air. A true vacuum, the kind that exists between stars, is a space with almost no matter in it at all. A few hydrogen atoms per cubic meter, drifting in enormous distances from one another, barely interacting across the span of years. No dense collections of molecules colliding rapidly. No medium through which kinetic energy can pass from particle to particle. In a true vacuum, there is almost nothing to be hot. This is the first piece of the answer to the question this video asks. If heat is molecular motion, and there are almost no molecules in the space between stars, then there is almost no heat in the space between stars. Not because warmth has been removed, but because the very material that would carry warmth is absent. You cannot have temperature without matter. Or rather, you can have a temperature, a technical one, measurable in specific ways, but it is not the warmth of conduction, of contact, of molecules passing energy from hand to stone. Think about sound for a moment. Sound is a wave, a pressure wave moving through a medium. When something vibrates, it pushes the air molecules around it, which push the molecules next to them, which push the next, and that cascade of pushed air eventually reaches your ear and you hear it. In a vacuum, there are no molecules to push. A bell ringing inside a sealed glass jar from which all air has been removed produces no sound you can hear. Not because the bell isn't vibrating, but because there is nothing to carry the vibration outward. The sound has nowhere to go. Heat by conduction works the same way. It needs a chain of molecules to pass energy along, and in deep space, that chain is broken. Not thinned, not weakened, broken. The gaps between the few particles that exist out there are so vast that conduction, as a mechanism of heat transfer, is essentially absent. This is not intuitive. We live inside a thick atmosphere on a warm planet orbiting a sun. Heat reaches us constantly and by multiple routes. We have no daily experience of a world where heat transfer simply does not happen the way we expect. Our intuitions about warmth are calibrated for this particular pocket of the universe, this thin, dense, warm exception. They do not generalize to the vast, cold majority. There is a moment in the history of early spaceflight, in the late 1950s, when engineers began to grasp this problem in practical terms. They had assumed, loosely, that heat management in space would resemble heat management on Earth, that things would warm up near the sun and cool down in shadow in roughly predictable ways. What they discovered instead was that spacecraft behaved in unexpected extremes, burning on sun-facing surfaces, falling to dangerous lows on shadowed ones, with almost no gradual transition between the two. Because there was no atmosphere to carry heat around the vehicle, to average out the temperature, to smooth the difference between sun and shadow. The vacuum was not a moderating presence, it was an absence, and the absence was the problem. It forced an entirely new field of engineering into existence: thermal management in space. Designing for a world where heat only moves by radiation, where conduction and convection play almost no role, where the difference between one side of a metal panel and the other can be 300 degrees depending on which way it faces. That problem has never fully gone away. Every spacecraft ever sent beyond Earth's atmosphere has had to solve it. Every mission to Mars, to Jupiter, to the edges of the solar system carries thermal blankets, heaters, radiators, precisely because the void does not manage temperature for you. What this means for tonight's broader question is simple. Space is cold not because nothing is producing heat. There are billions of stars producing extraordinary amounts of heat in every direction. Space is cold because heat cannot travel through nothing. And space is, in the most profound sense, the largest concentration of nothing that exists. The stars burn, the light leaves, and the light crosses an emptiness so complete that the warmth it carries only matters when it finally meets something solid enough to receive it. And the question that follows naturally from this, the one that deserves its own careful attention, is how heat travels through space at all, if conduction and convection are absent. The answer is radiation. And the answer to why radiation is not enough to warm the void is where this gets genuinely strange. There are three ways heat moves. Three and only three. And physics has been very clear about this for a long time. The first is conduction, the direct transfer of energy between molecules in contact. The warmth that flows from a hot pan into the handle, from pavement into the soles of bare feet on a summer afternoon. The second is convection, the movement of heated fluid or gas carrying energy from one place to another. The warm air rising from a radiator, the ocean currents redistributing warmth across hemispheres. The third is radiation, the emission of electromagnetic waves that carry energy through space without needing any medium at all. In the world you inhabit, all three operate simultaneously. The warmth of a room reaches you through conducted heat in the floor beneath your feet, through convecting air currents moving across your skin, and through radiated infrared energy from every warm object around you. Your body does all three at once, constantly. You radiate heat into the room, conduct heat into anything you touch, and convect warmth into the air you disturb with movement. Heat management on Earth is a symphony of all three mechanisms playing at once. Space removes two of those three mechanisms entirely. Conduction requires contact, molecules touching molecules, passing energy along a chain. In interstellar space, the nearest molecules may be separated by distances measured in kilometers. There is no chain. There is no contact. Conduction, as a mechanism of warmth, simply does not function in a medium this sparse. You could place two objects a centimeter apart in interstellar space, and almost no heat would conduct between them, because the bridge of matter needed to carry that energy does not exist. Convection requires a fluid, a gas or liquid, dense enough to carry energy as it moves. Space has no such fluid. The thin scattering of hydrogen atoms in the interstellar medium cannot circulate, cannot rise and fall with temperature gradients, cannot carry warmth from one region to another the way a warm current of air moves across a room. The interstellar medium is a near-perfect vacuum. It does not flow the way fluids flow. What remains is radiation. Radiation is different from the other two mechanisms in a way that is genuinely remarkable. It requires nothing. No molecules, no contact, no medium of any kind. It is electromagnetic energy, photons, moving at the speed of light through absolute emptiness. The sun radiates energy across 93 million miles of vacuum, and that energy arrives at Earth without needing any material to carry it. In this sense, radiation is the only heat transfer mechanism that is native to the void. It belongs there. The other two are Earth mechanisms, adapted to dense matter. Radiation is the one that works in nothing. But here is what radiation cannot do. Radiation cannot warm a space. It can only warm a surface. Consider what happens when a photon leaves the sun. It travels outward at the speed of light, 186,000 miles per second, crossing the vacuum. While it is traveling, it is not warming anything. The space the photon moves through is not heated by its passage. The photon carries energy, but energy in transit is not temperature. Temperature is what happens when that energy is absorbed by matter and converted into molecular motion. Until the photon meets something solid, a planet, a dust grain, an atmosphere, a spacecraft hull, it does not produce warmth. It is simply light, moving in silence through cold nothing. This is the distinction that most explanations of space temperature skip over, and it is the one that makes everything else make sense. Radiation is real. The sun's radiation is intense, but intensity of radiation across a vacuum does not produce a warm vacuum. It produces light crossing cold emptiness until it strikes something. Imagine a single candle in an enormous dark room, a room the size of a city, with smooth walls made of perfect mirrors. The candle radiates in all directions. Its light bounces off every surface and fills the room with a faint glow. But the air in that room is not heated by the light bouncing through it. The air temperature barely changes. What gets warmer is whatever is close to the candle and absorbs the radiation directly. Stand near the flame and you feel warmth. Walk to the far wall and the air around you is nearly the same temperature it was before the candle was lit. The light fills the room. The warmth does not. Space is that room, except the room is approximately 93 billion light years in diameter. The candle is a star, and the air is so thin it barely exists. There is a way to measure this precisely. In orbit around Earth, on the side facing the sun, a spacecraft hull reaches temperatures of around 120 degrees Celsius. The radiation from the sun, arriving at full intensity at this distance, drives the surface that hot. Now rotate the spacecraft. The side facing away from the sun drops toward minus 160 degrees Celsius or lower. Same orbit, same spacecraft, same distance from the sun. The difference is 280 degrees, because one side is absorbing radiation and one side is radiating it away into the void. The void itself is not warm. Only the surfaces exposed to incoming radiation become warm. And the moment they stop being exposed, they begin radiating their own energy outward and cooling rapidly. What this tells you is that warmth in space is a local, surface phenomenon. It is not distributed through the medium the way warmth is distributed through Earth's atmosphere. On Earth, the air averages out temperatures across enormous regions. The atmosphere absorbs radiation, distributes it through convection, holds it in through the greenhouse effect, and creates the relatively stable band of temperatures in which life exists. That averaging mechanism, that distribution system, does not exist in the void. In the void, warmth is wherever radiation is currently hitting matter, and nowhere else. For context, the temperature of interstellar space, away from any star, in the regions between star systems, is approximately 3 Kelvin. 3 degrees above absolute zero. In Celsius, that is minus 270 degrees. In Fahrenheit, minus 454 degrees. This is not a region-specific measurement. It is approximately the background temperature of the universe itself, the faint residual warmth of the Big Bang, spread evenly across all of space in every direction. Wherever you go in the cosmos, wherever there is no local source of radiation striking a surface nearby, the temperature falls toward this baseline, 3 Kelvin, almost nothing. And here's the weight of that number. Liquid nitrogen, the substance used to freeze things instantly in laboratories, the thing that boils dramatically when poured on the floor, liquefies at 77 Kelvin, 77 degrees above absolute zero. This already seems extraordinarily cold. Interstellar space is 25 times colder than that. The temperatures we use for industrial freezing, for preserving biological tissue, for experiments at the edge of what matter can survive, all of them are warm compared to the baseline temperature of the space between stars. You might think the sheer number of stars in the universe would change this. 2 trillion galaxies, each containing hundreds of billions of stars, each pouring out radiation in all directions. Surely the combined light of all those stars warms the void between them to something above 3 Kelvin. The answer is almost no. The universe is too large. The stars are too far apart. Their combined radiation, distributed across the full volume of observable space, does not appreciably raise the background temperature. The void wins, simply by being so much more of the universe than the stars are. What radiation needs to produce warmth is a receiver, a surface, a body, a world. And those are vanishingly rare across the total volume of space. The light is everywhere. The warmth is almost nowhere. Which raises the next question quietly. If radiation is the only mechanism that works in space, and radiation only warms surfaces, and the universe has so few surfaces relative to its total volume, then how does the sun warm Earth as thoroughly as it does? The answer lies in something Earth has that almost nothing else in the solar system has in quite the same way. An atmosphere capable of holding what radiation delivers. And what the moon teaches us about what happens without one is something worth staying with for a while. The moon is 238,000 miles from Earth. At that distance, it receives almost exactly the same amount of solar radiation Earth does. The same sun, the same distance, near enough. The same photons arriving at the same intensity, striking a surface with the same ancient light. In every relevant sense, the moon sits in the same thermal position Earth occupies relative to the sun. And on the moon, the temperature in full sunlight reaches 127 degrees Celsius. Hot enough to boil water, hot enough to blister. The surface absorbs solar radiation directly, with nothing above it to reflect or redistribute or moderate the incoming energy, and it heats accordingly. Stand on the sunlit surface of the moon without a spacesuit, and the radiation alone would be catastrophic. Step into shadow, behind a boulder, into a crater that hasn't seen direct sunlight in 1,000 years, and the temperature falls to minus 173 degrees Celsius. A difference of 300 degrees in the space of a single footstep. Not gradually, not over time, in the length of a shadow. There is no atmosphere on the moon to average this out. No air to absorb solar energy and carry it around the surface into the shade. No greenhouse effect to trap heat at night and hold the temperature above freezing until morning. No convection, no circulation, no thermal blanket. Just rock exposed directly to radiation on one side, and rock radiating its stored energy into the void on the other. The result is a world of impossible extremes sharing the same orbital address. This is what radiation alone produces. Not stable warmth, not distributed warmth. Intense local heat wherever the radiation strikes directly, and almost absolute cold everywhere else. Understanding this required some painful learning in the early years of space exploration. The assumption among engineers in the 1950s and early 1960s was that spacecraft would warm up predictably near the sun and cool down predictably in shadow. The thermal environment of space was imagined as something like a cold room, consistently cold, requiring heaters to keep instruments working, perhaps a bit of insulation here and there. The vacuum was expected to behave something like a refrigerator, holding a steady, low temperature throughout. What they discovered was something entirely different. The first American satellites experienced thermal crises that had not been anticipated. Some overheated on sun-facing sides while freezing on shadowed ones. The temperature gradients were violent. Electronics designed to work within reasonable ranges failed because the range in space was not reasonable. A spacecraft in Earth orbit can experience a temperature swing of more than 250 degrees Celsius simply by moving from sunlight into shadow, a transition that happens multiple times per hour in low orbit. NASA and its engineers had to build an entirely new discipline around this problem. Thermal control systems became one of the most complex engineering challenges in spacecraft design. Multi-layer insulation blankets, the thin, crinkled gold and silver foil you see covering satellites, are not there to keep the spacecraft warm. They are there to manage radiation exchange precisely, to control how much energy the spacecraft absorbs and how much it re-radiates into the void. The goal is not warmth. The goal is stability in an environment that provides none naturally. The deeper principle at work here is called the inverse square law. It is one of the most important relationships in physics, and it governs how radiation spreads through space. When a source emits energy in all directions, as stars do, that energy spreads outward across an ever-expanding sphere. The surface area of a sphere grows with the square of its radius. Double the distance from a source, and the energy is now spread across 4 times the area. Triple the distance, and it spreads across 9 times the area. At 10 times the distance, 100 times the area. What this means in practice is that the intensity of solar radiation falls off with extraordinary speed as you move away from the sun. At Earth's distance, 1 astronomical unit, solar intensity is approximately 1,361 watts per square meter. That is the number that drives all of Earth's weather, all of its seasons, all of the energy in every ecosystem on the planet's surface. At Mars, about 1.5 astronomical units from the sun, solar intensity has dropped to around 590 watts per square meter, less than half. At Jupiter, 5 astronomical units out, it falls to approximately 50 watts per square meter. At Neptune, 30 astronomical units from the sun, it is roughly 1.5 watts per square meter, barely more than 100th of what Earth receives. And at the outer edge of the Oort cloud, where the sun's influence fades into the background of deep space, solar intensity has dropped to essentially nothing. The sun, from that distance, is a slightly brighter star among many. Its radiation, once the dominant fact of local physics, has been diluted by the inverse square law into a whisper. Beyond the solar system entirely, in the interstellar medium that stretches between star systems, you are beyond the reach of any one star's warmth. The combined radiation of all nearby stars provides a faint, diffuse background, but it is not enough, not remotely enough. At those distances, the temperature of space falls back toward the baseline that fills the universe everywhere, the cosmic microwave background, sitting at approximately 2.7 Kelvin. Consider what that number means in human terms. 2.7 Kelvin is 2.7 degrees above the coldest temperature that physics permits to exist. Absolute zero, 0 Kelvin, is the point at which all molecular motion stops entirely. There is no colder. It is not a practical limit that better technology might one day overcome. It is a fundamental boundary of physical reality. And the baseline temperature of the universe, the temperature that fills all of space in all directions when no local star is close enough to warm it, sits a mere 2.7 degrees above that fundamental boundary. 2.7 degrees. That is the gap between the temperature of the universe at large and the coldest thing that can exist. On a scale of billions of degrees, the temperature of stellar cores, of supernovae, of the early universe, that gap is essentially nothing. The universe, at its baseline, is almost as cold can be. And this raises the question that has been waiting underneath everything said so far. If the universe has this baseline, this cold floor that fills all of space, and if stars are burning at millions of degrees in their cores, Why does the gap between them still sit at almost nothing? Why don't the stars fill space with warmth? Why, with 2 trillion galaxies and hundreds of billions of stars each, is the void still almost absolute zero? The answer is scale. And scale, when you apply it honestly to the universe, is not a concept that resolves into comfort. In 1964, two radio astronomers at Bell Laboratories in New Jersey were trying to eliminate noise from a large horn antenna they had built to track early communication satellites. The antenna was sensitive, and it was picking up a faint background hiss, a persistent, directionless signal that seemed to come from everywhere at once and from no identifiable source. They checked the equipment, they recalibrated, they cleaned the antenna. At one point, they removed a pair of pigeons that had roosted inside the horn and carefully cleaned out what they delicately described in their notes as white dielectric material. The noise did not go away. Arno Penzias and Robert Wilson had discovered the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. They had found it by accident while trying to get rid of it. What they were detecting was electromagnetic radiation, specifically microwave radiation, filling the entire universe uniformly in every direction. It has been there since approximately 380,000 years after the Big Bang, when the early universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms. Before that moment, the universe was so hot and dense that it was opaque, a plasma through which light could not travel. After that moment, the universe became transparent, and the light that had been trapped inside it was released. That light has been traveling ever since, in all directions, filling all of space, gradually cooling as the universe expanded. Today, that radiation has cooled to 2.7 Kelvin. It is everywhere, not in some regions and not others, not concentrated near galaxies or absent in voids, everywhere. Every point in space, in every direction you can point a sensitive antenna, receives this radiation equally. It is the most uniform thing in the universe. Its temperature varies by less than 1 part in 100,000 from one part of the sky to another. It fills the cosmos like a bath that has no edges, no hotter corners, no cooler depths. Just 2.7 Kelvin, uniformly in every direction, across every distance. What this means physically is that any object placed in interstellar space, any object removed from the influence of a nearby star, will eventually cool toward 2.7 Kelvin. Not toward zero, toward 2.7 Kelvin, because the CMB is always there, always radiating a tiny amount of energy into every surface. The CMB is the floor. Nothing in the observable universe can cool below it, because the CMB never stops providing that faint minimum warmth. But 2.7 Kelvin, to be clear about what it represents, is not meaningfully warm. It is the warmth of a universe that has been expanding and cooling for 13.8 billion years, and it has nearly finished cooling. It has nearly reached the state where temperature, as a concept, stops having meaningful distinctions. Warmth requires a gradient, a difference between a hotter place and a cooler place, a flow of energy from one toward the other. At 2.7 Kelvin, the gradient that fills the universe is barely distinguishable from nothing. To understand absolute zero is to understand what this number is close to. Absolute zero, 0 Kelvin, minus 273.15 degrees Celsius, minus 459.67 degrees Fahrenheit, is the temperature at which molecular motion ceases entirely. not slows dramatically, seizes. There is no thermal energy to transfer, no vibration, no kinetic activity in the particles of matter. This is not merely very cold. This is the thermodynamic ground state. Nothing can be colder because coldness is defined by the absence of molecular motion, and at 0 Kelvin there is none. In a laboratory, physicists have cooled small systems to within billions of a degree of absolute zero. These are some of the coldest places in the known universe, colder than deep space, colder than the surface of Pluto, colder than anything that exists naturally anywhere in the cosmos. Achieving this requires extraordinary technology and enormous effort. It is not something the universe produces on its own. The universe's natural baseline, 2.7 Kelvin, is 2.7 degrees above this absolute floor. On any intuitive scale, that is very close to nothing. It is the temperature of a universe that has been cooling since its violent beginning and has nearly run out of warmth. And this is where the question this video asks comes into focus most sharply. The universe has 2 trillion galaxies. The observable universe alone, the portion we can see, contains somewhere between 100 billion and 400 billion stars just in our own Milky Way. And that galaxy is one of 2 trillion. The total number of stars in the observable universe is estimated at around 200 sextillion, a 2 followed by 23 zeros. Each of those stars is a nuclear furnace, burning at temperatures ranging from a few thousand to tens of millions of degrees. They have been burning for billions of years. They pour energy into space in all directions, continuously, without pause. And the baseline temperature of the universe is 2.7 Kelvin, 200 sextillion stars. And the void between them sits 2.5 degrees above the coldest temperature that physics permits. This is not a paradox. It is not a contradiction. It is a consequence of scale so vast that intuition simply cannot process it. But we can approach it. We can give it form. Imagine the entire observable universe compressed to the size of the Earth. On this scale, the stars, those 200 sextillion furnaces, would be smaller than atoms. The space between them would still be enormous, because the space between stars, even at this scale, vastly exceeds the space occupied by the stars themselves. Stars are extraordinarily rare objects. They exist in galaxies, yes, and galaxies contain hundreds of billions of them. But galaxies themselves are separated by millions of light years of empty intergalactic space. The universe is almost entirely nothing, with a very thin scattering of burning points distributed through that nothing. When you account for this, when you calculate the total energy output of all stars and distribute it across the total volume of space, the energy density drops to almost nothing. The universe is too large. It has been expanding faster than starlight can fill it. There are regions of space from which the light of any star has not yet had time to arrive, because those regions are expanding away from us faster than light can cross them. The universe, in a very real sense, is outrunning its own warmth. The cosmic microwave background, the 2.7 Kelvin bath that fills all of space, is the most honest answer to the question of what the universe's temperature is. Not the temperature of stellar cores, not the temperature of supernova remnants or the centers of active galaxies. Those are local phenomena. brief and rare in the context of the whole. The temperature of the universe, taken as a whole, is 2.7 Kelvin, and it is falling. As the universe expands, the CMB cools. 1 billion years from now, it will be slightly colder. In 1 trillion years, it will approach a value so close to absolute zero that the distinction barely matters. Cold is not a condition the universe finds itself in temporarily. Cold is what the universe is moving toward, has always been moving toward, since the moment its initial heat began to spread across the expanding fabric of space. The stars are not winning. They are exceptions, burning brightly against a background that dwarfs them in every dimension, in volume, in duration, in the final state toward which everything trends. Penzias and Wilson received the Nobel Prize in Physics in 1978 for their discovery. The pigeons were relocated, and the hiss they had tried so hard to remove, that directionless, sourceless whisper coming from everywhere at once, turned out to be the oldest light in the universe, the fading echo of creation itself, now cooled to a temperature that is almost indistinguishable from the silence of perfect cold. What the CMB tells us is that the universe has a memory of warmth, and that memory is very faint and growing fainter. The stars burn on, but around them, in the vast reaches that separate them, the universe has already mostly forgotten what warmth was. The next question follows directly from this. If the stars produce so much energy, and if that energy spreads outward in all directions, at what point does a star's influence simply run out? At what distance does even a bright, active star like the Sun become irrelevant to the temperature of the space around it? The answer, when you work through the numbers, comes much sooner than most people expect. The Sun is not a modest object. At its core, the temperature reaches approximately 15 million Kelvin, a number so far beyond ordinary experience that it requires a moment of stillness to absorb. The surface, cooler by comparison, still sits at around 5,778 Kelvin. In plain terms, the surface of the Sun is nearly 6,000 degrees. It is bright enough that looking directly at it for even a fraction of a second causes permanent retinal damage. It pours out energy at a rate of 3.8 times 10 to the 612 watts. That is 380 yotawatts, a number with 26 zeros behind it, a figure that has no comparison in human experience. Every second, the Sun converts approximately 4 million metric tons of mass directly into energy through nuclear fusion. And yet, 4.2 light-years away, in the direction of the nearest star, the Sun's influence on the temperature of interstellar space has faded to essentially nothing. A spacecraft sitting in deep interstellar space, equidistant between the Sun and the next nearest star, would be bathed in a combined stellar radiation so faint that its equilibrium temperature, the temperature it would reach sitting in that radiation, would be only slightly above the cosmic microwave background. Somewhere between 4 and 10 Kelvin, depending on the exact location. For all practical purposes, interstellar space is at the CMB temperature, because no star is close enough to raise it meaningfully above that baseline. How does this happen? How does a star producing 380 yotawatts of energy manage to warm only the immediate thin shell of space around it, leaving the vast darkness beyond almost undisturbed? The inverse square law does the arithmetic. Solar intensity at Earth's distance, 1 astronomical unit, approximately 93 million miles, is 1,361 watts per square meter. That intensity has already spread across a sphere with a radius of 93 million miles. But it is still powerful enough to drive weather, sustain photosynthesis, and create the thermal conditions for liquid water. It is, at that distance, still a dominant physical fact. At the distance of Neptune, 30 astronomical units from the Sun, solar intensity has fallen to about 1.5 watts per square meter. Earth receives nearly 1,000 times more energy per square meter from the Sun than Neptune does. Neptune's average temperature is around 72 Kelvin, cold beyond anything on Earth's surface, but still far warmer than interstellar space. At the outer edge of the Oort cloud, the diffuse shell of icy objects that marks the outermost boundary of the solar system, roughly 100,000 astronomical units from the Sun, solar intensity has dropped by a factor of 10 billion compared to Earth. 10 billion. The Sun, from that distance, is simply the brightest star in the sky, not meaningfully brighter than several others. Its contribution to the local temperature is almost indistinguishable from that of other nearby stars. Beyond that, in the interstellar medium, the space between solar systems, you are in a region that receives the combined radiation of every nearby star, distributed across the vast distances between them. The nearest star to our Sun is Proxima Centauri, 4.24 light-years away. 1 light-year is approximately 5.88 trillion miles. 4.24 light-years is roughly 25 trillion miles. At that distance, Proxima Centauri's radiation has spread across a sphere with a radius of 25 trillion miles. The energy density is almost unmeasurable. Its contribution to local temperature is a fraction of a Kelvin above the CMB. Now consider that between the Milky Way and its nearest large neighbor, the Andromeda Galaxy, the distance is approximately 2.5 million light-years. That gap between one galaxy of 300 billion stars and another is filled with almost nothing. Temperatures there are extremely close to the CMB baseline. No star is close enough to matter. No radiation is intense enough to make a meaningful difference. The intergalactic medium is one of the coldest places in the universe precisely because it is one of the furthest from any source of warmth. This is scale working as physics, not as metaphor, not as illustration, but as the literal mechanism by which the universe maintains its coldness despite containing an almost incomprehensible number of burning stars. The stars are numerous. Space is more numerous still. The volume of the observable universe, estimated at approximately 4 times 10 of the 8th cubic meters, is so staggeringly large that even 200 sextillion stars distributed through it are separated by distances that the inverse square law reduces to effective irrelevance. To put this in a form that can be held more easily, imagine you are standing in a room the size of a continent. In the center of the room is a single lit candle. At the edges of the room, the light from that candle is so faint that measuring it requires sensitive equipment. The air at the edges is not warmed by the candle at all. It is at the ambient temperature of the room. The candle is real. The candle is burning, but the room is too large for the candle to matter. Now make the room the size of the observable universe. Make the candle a star. Make there be 200 sextillion candles. And recognize that even with that many candles, the room is so much larger than all of them combined that the ambient temperature, the temperature away from any individual candle, barely rises above the baseline. The room wins. It has always won. It will always win. There is a concept in cosmology called Olbers' paradox, named for Heinrich Wilhelm Olbers, a German astronomer who posed the question in 1823. If the universe is infinite and filled with stars, why is the sky dark at night? In an infinite universe with uniform star distribution, every line of sight should eventually terminate at a star. The sky should be as bright as the surface of a star, blindingly, uniformly bright in every direction. The fact that the night sky is dark is itself a puzzle. The resolution involves the finite age and expansion of the universe. The universe has not existed long enough for light from infinitely distant stars to reach us. Many stars are so far away that their light is still traveling toward us and has not arrived. And the expansion of the universe stretches that light to longer and longer wavelengths as it travels, reducing its energy, cooling it toward the microwave background. The universe is not infinitely old, and it is expanding, and these two facts together ensure that the sky is dark, that starlight cannot fill the cosmos with warmth, that the baseline temperature of space remains close to 2.7 Kelvin and not something much higher. The dark night sky is not a coincidence. It is a direct expression of the universe's thermodynamic state, and that state is cold. Vast and cold, with rare warm exceptions distributed thinly through an ocean of dark. The exceptions are where we live. The exceptions are every world, every atmosphere, every ocean. The exceptions are what made chemistry into biology. The exceptions are everything. But they are exceptions. They are not the rule. And understanding them as exceptions, understanding that the cold is the default and the warmth is the deviation, changes what it means to find warmth here. On this planet, breathing this air, listening to these words in whatever warm place you have chosen tonight, you are not simply in a world. You are inside one of the universe's rarest accidents. You are inside the exception. How rare that exception is, how thin the margin, how specific the conditions required to produce it, is the next part of this. 3 Kelvin is a number. Like any number, it sits quietly on a page and asks nothing of you. But what 3 Kelvin actually does, what it means for matter to exist at that temperature, is something worth dwelling in for a while. Not because the information is urgent, but because numbers this extreme deserve to be felt, not just noted. Absolute zero is the floor. 3 Kelvin sits 3 degrees above it. In the vocabulary of temperatures humans encounter in daily life, this is not a distinction that makes intuitive sense. You have probably experienced -20 Celsius, bitter, biting cold that makes exposed skin ache within minutes. You have heard of liquid nitrogen at -196 Celsius, the substance that freeze-brands livestock and preserves biological tissue, and flash freezes the surface of whatever it touches in seconds. Both of these feel impossibly cold when described. Both of them are warm compared to the space between stars. Liquid nitrogen exists at 77 Kelvin. Interstellar space is at approximately 3 Kelvin. The nitrogen that freezes things on contact, that boils dramatically when it meets room temperature air, that is used to preserve human embryos, that nitrogen is more than 25 times warmer than interstellar space. To get from liquid nitrogen's temperature down to the temperature of the interstellar medium, you would have to remove more than 96% of its remaining thermal energy. It is not a small difference. The gap between liquid nitrogen cold and space cold is larger, thermodynamically, than the gap between liquid nitrogen and a warm summer afternoon. What does matter do at 3 Kelvin? Most gases have long since solidified or simply frozen into immobility. Nitrogen solidifies around 63 Kelvin. Oxygen freezes at about 54 Kelvin. Carbon dioxide solidifies at 194 Kelvin. That is already dry ice, the thing that makes fog in theatrical productions. All of those substances at interstellar temperatures are not gases or liquids. They are cold solids, barely moving, with almost no thermal energy left to transfer. Hydrogen and helium, the most abundant elements in the universe, remain gaseous at these temperatures, but at densities so low that the few atoms present are separated by distances measured in astronomical units. What cold this deep means for a human body is one of the most consistently misunderstood things in the depiction of space. Popular imagination, film, television, casual description tends to present death in the vacuum of space as freezing, the body stiffening, breath crystallizing, a rapid transition to something ice-like and still. This is not accurate, and understanding why it is not accurate reveals something important about how heat transfer actually works in vacuum. Freezing, as a process, requires conduction, something cold drawing heat from a warmer body through direct contact. Ice freezes your skin because the ice is touching your skin and absorbing your body's heat through molecular contact. The cold pavement freezes your feet because the pavement is conducting heat away from them. Freezing is fundamentally a conductive process. In a vacuum, conduction does not occur. There is nothing to touch the body, nothing to draw heat away by contact. What happens instead is that the body's heat radiates away as infrared radiation, slowly, far more slowly than most people imagine. An unprotected human body in the vacuum of space, at the temperature of interstellar space, would radiate its heat away over the course of minutes to hours, depending on the exact conditions. The process is not violent. It is not dramatic. It is a quiet dimming. But before cooling has time to become the primary concern, something else happens. The vacuum itself does the damage. Without external pressure, the gases dissolved in the body's tissues and fluids begin to come out of solution. Saliva on the tongue begins to boil, not because the mouth is hot, but because boiling point depends on pressure, and without pressure, water boils at body temperature. The lungs, if they hold air, risk rupture as that air expands outward into the vacuum. The skin puffs slightly. The blood does not boil, held in by the body's own pressure, but the softer tissues swell. This process, ebulism, the formation of gas bubbles in bodily fluids due to low pressure, would begin within seconds. It is the vacuum doing its work, not the cold. The cold comes later, gradually, as the body continues to radiate its heat into the surrounding space with nothing to replace it. Hollywood prefers the dramatic freeze, the slow motion crystallization, the stiffening form, the tragic dignity of it. But the truth is slower and stranger. The cold is patient. In a vacuum, it always has time. For objects rather than bodies, for metal, for rock, for the material that makes up spacecraft, the experience of interstellar cold is a gradual, deep settling. Materials contract. Metals become brittle in ways they are not at room temperature. Lubricants designed for Earth-normal conditions solidify. Electronics behave differently when thermal energy has been stripped away. The engineering of anything meant to survive deep space requires accounting for materials that are essentially at absolute zero. And materials at absolute zero are different from their familiar selves. Imagine for a moment what it would feel like to hold your hand open in interstellar space. Not the vacuum of low Earth orbit, where the sun's radiation would still heat the sunward side of your skin, where you are still within the thermal influence of a nearby star. True interstellar space, 3 Kelvin. The radiation arriving from all directions would be vanishingly faint. The CMB, which your body, with its thermal mass, would absorb without any noticeable effect. No star close enough to warm you. No conductive medium to pull heat from your skin. Just the slow, quiet radiation of your body's warmth outward into nothing. You would not feel the cold of space against your hand. You would feel the absence of everything that makes warmth possible. You would feel, or more precisely, your skin would begin the process of losing heat to nothing. Not to cold, to the absence of competition for the warmth you already carry. The distinction matters. Space is not cold the way a glacier is cold. A glacier is cold because it is dense matter at low temperature, and when you touch it, heat flows rapidly from your warm body into its cold mass. Space is cold because there is essentially nothing there. When you lose heat in space, it is not because the cold is taking it. It is because you are radiating it outward, and there is nothing sending any back. This is the existential version of the vacuum problem. On Earth, every environment participates in your warmth. The air, the ground, the objects around you, all of them are exchanging energy with you constantly. Some are cooler and absorb your warmth. Some are warmer and contribute to it. The system is in dialogue. In interstellar space, you are radiating into a listening absence. The universe is not cold toward you in any active sense. It is simply not there to respond. And yet, for all this, there is something paradoxical waiting at the nearest star. The Sun, the object whose warmth drives all of life on this planet, has a mystery coiled around it that has confused physicists for decades. As you move away from the solar surface, the temperature should drop. That is what thermodynamics predicts. Energy dissipates with distance. But that is not what the Sun does. Just above its surface, in a region called the corona, the temperature does not fall. It rises, dramatically, impossibly, by a factor of several hundred. And this paradox, the Sun growing hotter as you move away from it, has something important to say about how heat actually behaves when radiation is the only mechanism available. The surface of the Sun, the photosphere, the bright disk you are warned never to look at directly, sits at approximately 5,778 Kelvin, nearly 6,000 degrees. This is an extraordinary temperature. It is hot enough to vaporize iron, to dissociate most molecules into their component atoms, to reduce any known material to plasma. It is the temperature we think of when we think of the Sun's heat, and it is, in ordinary terms, beyond comprehension. Just above this surface lies a thin region called the chromosphere. Here, temperatures rise slightly to perhaps 10,000 Kelvin at its upper edge. Already this is puzzling, since thermodynamics tells us heat flows from hotter regions to cooler ones, not the other way around. But the chromosphere is thin, and the temperature rise is modest enough that it was noted without much alarm for many years. Beyond the chromosphere lies the corona, the Sun's outer atmosphere, visible to the naked eye only during a total solar eclipse, as a pearlescent halo, extending millions of kilometers into space. The corona is beautiful in photographs. It is also, by any rational thermodynamic expectation, impossible. The corona's temperature is between 1 and 3 million Kelvin, not 6,000 degrees, not 10,000 degrees, 1 to 3 million degrees. The outer atmosphere of the Sun, the part furthest from the nuclear furnace in its core, is between 200 and 500 times hotter than the surface directly below it. This violates the intuition that every person carries about how heat works. If you hold a candle, the flame is hottest at its base and cooler toward the tip. If you heat one end of an iron rod, the far end is cooler. Heat flows from the source outward, and as it flows, it dissipates. This is not an assumption. It is a fundamental principle of thermodynamics, and the Sun appears to violate it. For most of the 20th century, this was one of the most persistent, unsolved problems in solar physics. The corona's extreme temperature had been measured, confirmed, refined. The mystery was not whether it was real. It was clearly real, but how it could be. What mechanism was adding energy to the corona after the radiation from the photosphere had already passed through it? What was heating the outer atmosphere while the inner atmosphere remained hundreds of times cooler? The leading explanation today, still not definitively confirmed, but supported by substantial evidence, involves magnetic reconnection. The Sun's magnetic field is not smooth or stable. It is tangled, loops and arcs and braided structures of magnetic flux that are constantly being twisted, stretched, and deformed by the turbulent convection beneath the surface. When oppositely directed magnetic field lines are pressed together, they can break apart and reconnect in new configurations, releasing stored magnetic energy explosively. This energy heats the surrounding plasma to extreme temperatures almost instantaneously. A second mechanism involves Alfvén waves, oscillations that travel along magnetic field lines like waves traveling along a taut string. These waves carry energy outward from the turbulent solar interior into the corona, where they dissipate and deposit their energy as heat. Both mechanisms, reconnection and wave dissipation, are real physical processes. The debate is about their relative contributions, not about whether they occur. What both mechanisms share is that they are not conductive heat transfer. The corona is not being heated the way a pot of water is heated by a stove, by contact with a hotter surface below it. It is being heated by magnetic and wave processes that operate independently of the temperature gradient below. It is, in this sense, an example of heat transfer that defies the simple model of warmth flowing from hot to cold. The corona paradox teaches something important about the relationship between radiation and warmth. The photosphere radiates at 5,778 Kelvin. That radiation travels outward, through the corona, through the solar system, eventually reaching Earth and other planets. But this radiation does not heat everything it passes through equally. The corona itself is nearly transparent to most of the photosphere's radiation, meaning the coronal plasma does not absorb much of the passing light. The radiation goes through the corona and keeps going. What heats the corona is not the radiation from below. What heats the corona are mechanical and electromagnetic processes operating within the corona itself. The warmth is local, generated in place, not inherited from the surface below. This is the same principle at work in the broader problem of why space is cold. Radiation does not heat the medium it passes through. It heats only the surfaces that absorb it. Photons from the Sun pass through the corona, through interplanetary space, through the upper atmosphere of Earth, heating none of it directly. What they heat is whatever they are finally absorbed by: a leaf, a paved road, the ocean, the top of a cloud. Radiation is not warmth in transit, it is potential warmth, waiting for something solid enough to receive it. The corona is warm because it has generated its own warmth through its own local processes. Interstellar space is cold because it has not. There is nothing there to generate local warmth, and the radiation passing through it from stars, following the inverse square law, has spread so thin by the time it fills interstellar volumes that it cannot raise the temperature of the sparse matter present by any meaningful amount. There is something almost poignant about the corona considered this way. Here is the sun, producing more energy than human minds can encompass, pouring radiation outward in all directions, and just above its own surface, its outer atmosphere is being warmed by an entirely different process. The sun's own light is not what warms the corona. The sun's magnetism warms it. The sun, in a sense, warms itself differently in different layers, through different mechanisms, and only one of those mechanisms, radiation, escapes outward into space. And that escaped radiation, magnificent as it is, extraordinary as its intensity at Earth's distance remains, does not penetrate the void. It crosses the void. Those are different things. A ship crossing an ocean does not warm the water beneath it. Light crossing space does not warm the space around it. Understanding the corona also recalibrates how we should think about the relationship between stars and the temperature of the universe. Stars are not space heaters in the ordinary sense, objects that radiate warmth into a room and raise the room's temperature uniformly. They are point sources of radiation in an inconceivably large medium, and the radiation they produce is too thinly spread, too diluted by distance, too reliant on absorption by rare solid surfaces to change the baseline temperature of the void that surrounds them. The corona burns at 1,000,000 degrees. 10 kilometers above its outer edge, a spacecraft in the solar wind encounters plasma at temperatures of hundreds of thousands of Kelvin. 100 million kilometers further out, the temperature of interplanetary space at Earth's distance is such that an unshielded surface in sunlight reaches 120 Celsius, while a shielded surface in shadow falls to -160. A few light years from the Sun, interstellar temperature approaches the CMB baseline of 2.7 Kelvin. The gradient is steep. The fall from the Sun's influence is faster than the scale of the universe makes it seem. And the universe has very few suns close enough to any given point in space to keep that point above the baseline. Which brings this back to the question of what it means that warmth in the universe is rare. Not just physically rare, measurably, quantifiably rare as a fraction of the total volume of space. The universe is cold almost everywhere for almost all of its history in almost all directions. The question of how warmth ever came to exist, how the conditions that allow for warmth were assembled in certain places, around certain stars, is the next question worth sitting with. If you took all the space in the observable universe that is genuinely warm, warm enough to sustain liquid water, warm enough for chemistry to proceed at the pace needed for biology, warm enough by any reasonable definition that a living thing might find hospitable, and you measured it against the total volume of the observable universe, the fraction you would arrive at is so small it has no practical name in ordinary language. The observable universe spans approximately 93 billion light-years in diameter. Its total volume is estimated at around 4 × 10 to the 80 moment cubic meters. Within that volume exist roughly 2 trillion galaxies, each containing hundreds of billions of stars. Around some of those stars orbit planets. Around some of those planets, at the right distance, in the right orbital configurations, with the right atmospheric conditions, temperatures sit within the narrow band that allows liquid water to exist on a surface. That band is roughly between 273 and 373 Kelvin, 0 to 100 degrees Celsius, the range within which water is liquid at standard pressure. It is a range of 100 degrees. In a universe where temperatures span from 2.7 Kelvin at the CMB baseline to approximately 10 to 34 squared Kelvin at the theoretical maximum, the Planck temperature, the hottest temperature physics permits, the habitable range occupies a fraction of the full spectrum, almost too small to express as a ratio. And even within that fraction, the volume of space that is actually warm at any given moment, the aggregate volume of all planetary surfaces sitting in the right temperature range, is vanishingly small compared to the cold void surrounding them. Planets are small. Stars are small. Even galaxies, enormous as they are mostly empty space between their stars. The warm surfaces of habitable planets, added together across the entire observable universe, would constitute a volume that is, relative to the total volume of space, essentially zero. This is not a poetic exaggeration. It is the honest arithmetic of the situation. Warmth is the rarest thing in the universe by volume. Almost all of the universe is cold. Almost all of it has always been cold. Almost all of it will be cold when the stars have finished burning and the last warmth has radiated away into the expanding dark. There are places in the universe where the cold is particularly absolute. The Boötes void is a region of space approximately 330 million light-years in diameter, located in the direction of the constellation Boötes. Within this enormous volume, there are almost no galaxies. Not few, almost none. Where a region of comparable size elsewhere in the universe might contain thousands of galaxy clusters, the Boötes void contains roughly 60 galaxies, most of them arranged around its edges. Its interior is nearly empty of stars, nearly empty of matter, and its temperature is essentially the CMB baseline. It is a cold, vast absence in an already cold and vast universe. The Boötes void is not unique. There are many such voids, enormous, dark, cold regions where the universe's matter has been pulled gravitationally into the filaments and sheets and nodes of the cosmic web, leaving behind nearly empty space. Between the bright filaments lies darkness, and in that darkness, the temperature is 2.7 Kelvin, or very close to it. The warmth concentrates in the filaments, in the galaxy clusters, in the halos around stars. The voids, which make up the majority of the universe's volume, are cold. Consider what it means for the universe to have 2 trillion galaxies and still be predominantly cold. Each of those galaxies contains hundreds of billions of stars. Each of those stars is burning at temperatures ranging from 2,500 Kelvin for the coolest red dwarfs to 50,000 Kelvin or more for the brightest blue giants. The energy output is almost beyond arithmetic, and yet the combined warmth of all those stars, distributed through a universe of sufficient size, does not raise the background temperature above 2.7 Kelvin. You might wonder, sitting with this, what it is about the universe that produced such a vast expanse of cold. The answer is partly its age and partly its expansion. In the very early universe, in the first fractions of a second after the Big Bang, the temperature was unimaginably high. The entire observable universe was compressed into a volume smaller than a proton, and its temperature was at or above the Planck temperature. Everything was plasma. Everything was heat. There was no cold. But the universe expanded. As it grew, its energy spread across a larger and larger volume. Temperature fell, dramatically at first, then more gradually, following a curve determined by the laws of thermodynamics applied to an expanding space-time. By the time the first atoms formed, approximately 380,000 years after the Big Bang, the temperature had fallen to around 3,000 Kelvin. By the time the first stars ignited, perhaps 100 million years later, the background temperature had fallen to a few tens of Kelvin. By now, 13.8 billion years later, it sits at 2.7 Kelvin. The universe has been cooling since the moment it began. The stars formed and began producing local warmth, but they are not winning against the expansion. The universe's expansion carries energy outward into larger and larger volumes, diluting the warmth produced by stars faster than the stars can produce it. In the long competition between stellar warmth and cosmic expansion, the expansion has always been ahead. You are sitting or lying somewhere warm right now, and perhaps this is the moment to simply notice that. There is warmth around you, temperature sufficient for water to flow, for air to be breathable, for the chemistry in your body to proceed at its necessary pace. You exist inside the CMB, as everything in the universe does. The 2.7 Kelvin radiation passes through you at this moment, as it always does, from every direction. And yet, you are warm, because you are inside the exception, because your planet is close enough to a star and wrapped in an atmosphere that holds enough of that star's warmth in place that the CMB's cold floor is irrelevant to your daily experience. That exception is what the next part of this is about. Not the cold, for a moment, but how the warmth that contradicts the cold was assembled. What had to be true? What specific, narrow conditions had to be met for any surface anywhere in this cold universe to be warm enough for anything interesting to happen on it? The moon sits 238,000 miles from Earth. The sun sits 93 million miles from Earth. And the moon is at essentially the same distance from the sun that Earth is, close enough that for the purposes of calculating received solar energy, the difference is negligible. The same star, the same distance, the same radiation arriving at the same intensity, and Earth has life, liquid oceans, and a relatively stable surface temperature that has remained within the habitable range for billions of years. The moon has baking sunlit rock and freezing shadowed craters and nothing else. The difference is not location. The difference is atmosphere. Earth is wrapped in a thin shell of gas, approximately 78% nitrogen, 21% oxygen, and a small fraction of other gases including carbon dioxide, methane, and water vapor. This shell is almost nothing, physically speaking. If Earth were the size of a standard classroom globe, its entire atmosphere would be thinner than the coating of lacquer on the globe's surface. It weighs approximately 5.15 times 10 to the 8,000 kilograms, enormous in human terms, vanishingly small relative to the mass of the planet it surrounds. And yet, this thin shell is the difference between a warm, living world and a radiation-scorched, temperature-extreme wasteland. The mechanism is called the greenhouse effect, and it is worth understanding clearly because it is one of the most important physical processes in the universe for anything interested in warmth. Solar radiation arrives at Earth primarily as visible light and near-infrared radiation, short wavelength energy that passes through the atmosphere relatively easily. This radiation strikes the surface and is absorbed, warming the ground and oceans. The warmed surface then re-radiates energy, but at a different wavelength. Warmed surfaces emit infrared radiation at longer wavelengths than the incoming solar energy, and certain gases in the atmosphere, primarily carbon dioxide, methane, and water vapor, are much more opaque to this outgoing long-wave infrared than they are to the incoming short-wave solar radiation. In simple terms, sunlight gets in easily. The warmth that sunlight creates gets out with difficulty. The atmosphere acts as a one-way filter, letting energy in and trapping a portion of it before it can escape into space. This is not a malfunction. This is what makes Earth warm enough for liquid water. Without the greenhouse effect, Earth's average surface temperature would be approximately minus 18 degrees Celsius, 0 degrees Fahrenheit, cold enough for the oceans to freeze solid. With it, the average surface temperature is approximately 15 degrees Celsius. The greenhouse effect is responsible for a 33-degree warming of Earth's surface. It is not an anomaly or a problem in itself. It is the mechanism that holds the sun's warmth in place long enough for life to use it. The moon has no significant atmosphere. The solar radiation that strikes the lunar surface warms it to 127 Celsius in full sunlight. But when that surface re-radiates its warmth as infrared, there is nothing to stop it. It radiates directly into space. The warmth does not accumulate. It does not spread across the surface through atmospheric convection. It simply leaves. And without incoming radiation, on the night side or in permanent shadow, the surface cools rapidly to minus 173 Celsius, because there is no atmospheric blanket to slow the departure of stored heat. This is why the moon's temperature range is so extreme and Earth's is so moderate. Not location, not solar intensity, atmosphere. Venus illustrates a different version of the same principle. Venus is closer to the Sun than Earth. Its average distance is approximately 108 million kilometers compared to Earth's 150 million kilometers. It receives about twice the solar intensity Earth does. But Venus also has the most extreme greenhouse effect in the solar system, an atmosphere composed almost entirely of carbon dioxide at a pressure 90 times that of Earth's, with an additional layer of sulfuric acid clouds that trap heat with extraordinary efficiency. Venus's surface temperature is approximately 465 degrees Celsius. That is hot enough to melt lead. It is hotter than the surface of Mercury, which is closer to the Sun but has almost no atmosphere. On Mercury, the sunlit side reaches about 430 Celsius, while the shadowed side falls to minus 180 Celsius. Venus, further from the Sun, maintains 465 Celsius on both its sunlit and shadowed sides, because the greenhouse effect is so powerful that heat is distributed evenly across the entire planet. The Sun's warmth goes in and does not come out. What these examples collectively demonstrate is that distance from the star is only one component of surface temperature. The other critical component, arguably more important for life, is what happens to the radiation after it arrives. How much is reflected back to space? How much is absorbed by the surface? How much of the absorbed warmth is trapped by the atmosphere versus radiated back out? Earth's balance is precise in ways that are difficult to fully appreciate. The planet reflects approximately 30% of incoming solar radiation back to space without absorbing it. This is Earth's albedo, contributed largely by clouds, ice, and bright surfaces. The remaining 70% is absorbed by the surface and atmosphere, warmed, and then slowly re-radiated as infrared. The greenhouse gases slow that re-radiation enough to keep the surface warm. The oceans store enormous quantities of heat and redistribute it through currents, moderating temperature extremes. The atmosphere transports warmth from the equator toward the poles, preventing the tropics from becoming lethally hot and the poles from becoming even colder than they are. Every one of these systems, albedo, greenhouse effect, oceanic heat storage, atmospheric circulation, is a mechanism for holding the sun's warmth in place. None of them creates warmth. They all manage and redistribute the warmth the sun delivers. And the balance between them has remained within the habitable range for approximately 4 billion years, long enough for simple life to begin and eventually to produce the complexity that led, eventually, to a species capable of wondering about it. This balance is not guaranteed. It is not written into the laws of physics as a permanent condition. It is the result of a specific atmospheric composition, a specific distance from a specific star, a specific planetary mass that can hold an atmosphere against gravity's pull, a specific geological history that has recycled carbon and regulated the greenhouse effect through volcanic activity and plate tectonics. Change any of these significantly and the warmth goes away, either lost to space or trapped in a runaway cycle that makes the surface uninhabitable in the other direction. What makes Earth warm is not the sun alone. It is the entire system, the sun providing energy, the atmosphere holding it, the oceans distributing it, the geology regulating it. The warmth is a collaboration between forces, maintained in a balance that has lasted billions of years, but is not permanent. And permanent, in the context of a universe that will exist for trillions of times longer than it already has, is a concept worth examining with some care. Because the balance Earth currently enjoys is a temporary arrangement. The sun that warms this planet is changing. And the change, though it operates on timescales that make human history look like the blink of an eye, is moving in one direction, toward an end of this particular warmth, toward a cooling that no atmosphere can prevent. The sun has been burning for approximately 4.6 billion years. In that time, it has consumed roughly half of the hydrogen in its core, fusing it steadily into helium, releasing the energy that warms this planet, drives its weather, and sustains every living thing on its surface. It will continue burning for approximately another 5 billion years. By the scale of human civilization, this is forever. By the scale of the universe, it is the middle of a life that is not, in the end, infinite. When the sun's core hydrogen is exhausted, the fusion reactions that sustain it will shift outward to a shell surrounding the depleted core. The core itself, no longer producing energy, will contract under gravity, heating up. The outer layers of the sun, responding to the increased energy output from the shell, will expand, slowly at first, then dramatically. The sun will become a red giant. Its radius will grow to somewhere between 100 and 200 times its current size. In the process, it will likely engulf Mercury and Venus, and may reach as far as Earth's current orbit. At this point, the question of whether Earth's surface remains habitable is moot. The sun's luminosity during the red giant phase will be hundreds of times its current value. Whatever water remains on Earth's surface will have long since boiled away, not during the red giant phase, but several billion years earlier, as the sun's steady brightening over its main sequence lifetime gradually increases Earth's surface temperature past the threshold for a runaway greenhouse effect. Earth will become Venus before the red giant phase begins. The warmth that life requires will have become the warmth that ends it. After the red giant phase, the sun will shed its outer layers in a series of pulses, releasing them as an expanding shell of gas and dust, a planetary nebula, glowing briefly as the ultraviolet radiation from the exposed core ionizes the surrounding material. The core itself, compressed to roughly the size of Earth, will remain. This is the white dwarf stage. Dense, no longer fusing, simply radiating the last of its thermal energy into space. A white dwarf cools slowly, extraordinarily slowly. The cooling timescale is measured in billions of years, eventually trillions. A white dwarf formed from the sun would start at a surface temperature of perhaps 100,000 Kelvin and cool over tens of billions of years toward temperatures that make it invisible. A black dwarf, no longer emitting visible light, gradually fading toward the temperature of the surrounding space. No black dwarfs are believed to exist yet in the current universe. The universe is not old enough. The most ancient white dwarfs still glow faintly, but given sufficient time, more time than the universe has yet existed, even these cooling embers will reach equilibrium with the CMB and fade to darkness. What this describes, scaled up to encompass all stars in the universe, is the concept known as the heat death of the universe. Not heat in the sense of warmth, but heat in the thermodynamic sense, entropy, the measure of disorder in a system. The heat death is the state toward which thermodynamics predicts all closed systems tend. Maximum entropy, thermal equilibrium, the end of all temperature gradients. Temperature gradients are what make things happen. When one region is warmer than another, energy flows from warm to cold, and that flow can do work. It can drive engines, power chemistry, sustain life. The sun is warm, space is cold. That gradient drives the weather on Earth, powers photosynthesis, sustains the entire biosphere. Stars are hot, the void is cold. That gradient across the universe drives stellar winds, supernova remnants, the heating of galactic gas. When there are no more gradients, when everything is at the same temperature, nothing happens. Nothing can happen. There is no flow, no work, no chemistry, no motion of consequence. The universe reaches a state of total thermal equilibrium, and in that state, change effectively ceases. The timescale for this is staggering. The current age of the universe is approximately 13.8 billion years, often written as 1.38 times 10 to the video game years. The heat death of the universe is estimated to occur at around 10 to the video game years, a Google years. Not billions, not trillions, not quadrillions. A number so large that all the words humans have for big numbers are inadequate. The universe we currently inhabit, the one that contains stars and galaxies and planets and life, is an infant. It is in the first fraction of a percent of its total lifespan, and in the vast majority of that lifespan, in the epochs beyond the death of the last stars, beyond the evaporation of the last black holes through Hawking radiation, beyond the decay of the last protons, the universe will be cold. Not the 2.7 Kelvin of today, but colder still, as the CMB itself continues to cool with the expansion of space, eventually approaching temperatures that make today's void seem warm by comparison. What this means is that the warmth we know, the warmth of the sun, of fire, of living bodies, is not merely rare in space, it is rare in time. We exist in an early, warm era of the universe. The universe was hotter before us, and it will be incomprehensibly colder after us. Not after humans, but after all stars, after all warmth, after any process that resembles what we call energy transfer. The cold that surrounds us in space is the future of everything, not just the void between stars. There is something in this that resists the word terrifying, though terrifying is what some people reach for first. It is too large, too slow, too absolute for terror to quite fit. Terror is for things that might happen to you. The heat death of the universe will happen to nothing, because by then, there is nothing left to happen to. It is more like the knowledge that the piece of music you are listening to will eventually end. Not in the next measure, not in the next movement, but eventually, in a silence that will outlast every listener by an incomprehensible span. The cold that fills space tonight, the 2.7 Kelvin baseline that surrounds every star and every planet and every living thing in the observable universe, is not an accident or a temporary condition to be overcome. It is the universe's direction of travel. It is what was always coming. What we are inside right now, this brief, warm, improbable middle, is the exception to a rule that will eventually reassert itself completely. And in the knowing of this, something shifts. Not despair, something quieter. The warmth you feel right now, whatever warmth is near you, whatever fire or sun or body heat or blanket is doing its small work against the cold, is doing something the universe did not require. It is producing warmth in a cosmos that tends, in the long end, toward its absence. That warmth does not know it is rare, but you do, and knowing changes what it means. Somewhere, at this moment, light is leaving a star. It left, to be precise, some number of years ago, perhaps 4, perhaps 4,000, perhaps 4 million. And what is happening now, at this moment, is that the light is arriving, striking something, a grain of dust at the edge of a solar system, the upper atmosphere of a moon no one has named, the hull of a spacecraft drifting in silence between worlds. The light crosses the vacuum without warming it. It crosses without knowing anything is cold. It carries energy, and that energy is real, and it will matter the moment it finds something to land on. Until then, it is simply light in the dark, crossing a cold it cannot perceive and does not change. This is the universe's daily work. This is what happens in every direction, at every moment, across the full volume of space in all its dimensions. Light crossing cold, warmth in transit, potential heat waiting for a surface. Most of it never finds one. Most of the light ever produced by every star that has ever burned will travel forever, or close enough to forever that the distinction cannot be felt without striking anything. The universe is too empty. The surfaces are too few. The photons sail outward into expanding dark, their energy real and present and useless, until the expansion of space stretches their wavelengths long, and the energy they carry falls toward nothing. Light that left a star billions of years ago, aimed at no particular destination, will continue traveling when the star itself has cooled. Will continue traveling when the galaxy it left has merged with others and the stars have burned out. Will continue traveling in the slow, expanding dark of a universe in its long old age. The cold is patient in a way that words like patient do not quite reach. It does not wait. It simply is and continues to be, while warmth comes and goes around it. Stars ignite and burn and cool and fade. Planets form and warm and eventually lose their heat or their stars and grow cold again. Life begins, somewhere, here at least, and perhaps elsewhere, and uses the warmth that is available, and burns and fades as stars do. The cold receives all of this without changing. It does not win, it simply remains. You are a warm thing in a cold universe. This is a precise physical description, not a metaphor. Your body maintains a temperature of approximately 37 degrees Celsius, 310 Kelvin. Against a CMB of 2.7 Kelvin, you are more than 100 times warmer than the baseline of the cosmos. You radiate heat into every room you occupy. You warm the space immediately around you. You are a small, improbable region of elevated temperature in a universe whose overwhelming tendency is toward the cold. Your warmth is not permanent. Nothing's warmth is. The energy your body uses to maintain its temperature comes from food, which comes from sunlight, which comes from the sun burning through its hydrogen at 15 million degrees. That chain is real, and it is long, and it is finite. The sun will not burn forever. Your body will not burn forever. But right now, in this moment, the chain holds. The warmth flows. The machinery works. There are perhaps 400 billion stars in the Milky Way. There are perhaps 2 trillion galaxies in the observable universe. Around some fraction of those stars orbit worlds that are warm enough. Around some fraction of those warm worlds, the conditions assembled: atmosphere, distance, geology, time, into something that could sustain chemistry. Around some fraction of those chemically active worlds, the chemistry went somewhere, became something, became anything. We know it happened here. We do not know if it happened elsewhere, but we know what it required. We know that warmth was necessary, that the specific, narrow, improbable warmth of a planet in the right place, wrapped in the right gases, orbiting the right star at the right distance for billions of years, that this warmth was the prerequisite. Without it, none of the chemistry proceeds. Without the chemistry, none of the biology. Without the biology, no one to notice that it is cold. The cold is vast. The cold is old. The cold predates every star and will outlast the last one. And in the middle of all of it, for a duration that is brief even by stellar standards, warmth gathers in small places and does extraordinary things. There is no crescendo here. That is not what this deserves. The universe does not crescendo. It continues, expanding quietly, cooling slowly, carrying its warmth in small pockets through a dark that goes on longer than any thought reaches. The stars do not know they are burning in the cold. The cold does not know the stars are there. These are not characters in a drama. They are conditions, settling into their long arrangement, moving toward an equilibrium that no one alive will ever see. But you are in it right now, this arrangement, this brief warmth inside the long cold. The CMB is passing through you at this moment, as it always is, from every direction, at 2.7 Kelvin. And you are 310 Kelvin, and the machinery in your cells is using the warmth the sun provided to keep that difference alive for another moment. That is not a small thing. Even if no one in the universe has counted it, even if the cold will not remember it, even if warmth, in the end, is what the universe is moving away from. Right now, in this moment, the machinery holds. The warmth is here. The exception is real. And the night continues. Walk outside on a clear night if you can, and stand still for a moment. The stars you see are not symbols of warmth. They are islands of warmth, small, burning, surrounded by cold so deep and so absolute that warmth, from any useful distance, is indistinguishable from its absence. The darkness between those points of light is not simply the absence of stars. It is a temperature. It is 2.7 degrees above the lowest temperature that physics permits. It is the universe's natural state, the condition it settles into when nothing local is burning. And yet you are warm. Your body, standing outside, is radiating heat into that cold night. Infrared light is leaving your skin right now, carrying warmth upward through the atmosphere, and in the small fraction that escapes, outward into the dark. You are contributing, in the most literal physical sense, to the heat output of this warm world. You are part of the exception. You have always been part of the exception. Every fire your ancestors lit, every sun-warmed stone they rested against, every living body that shared warmth in the dark, all of it has been the exception. Warmth was never the default. It was always the local, temporary, improbable arrangement of conditions that produces heat where the universe would otherwise have none. The question this video began with, why space is cold even though the stars are burning, has an answer now. Not one answer, but several layers of the same answer. Heat requires matter to travel through matter, and the void has almost none. Radiation crosses the void but warms only the surfaces it strikes, not the space between. The inverse square law ensures that even the most powerful star's warmth fades to nothing within a fraction of a light year. The universe is too large and too old for its stars to raise its baseline temperature above the ancient, cooling glow of the Big Bang's afterglow. Cold is not a condition that happened to the universe. Cold is what the universe is, beneath and beyond and around every exception. The stars burn in it, the planets warm within it. Life, in at least one corner, noticed it. You are a warm body in a cold cosmos, listening to the dark on a world that has managed, for 4 billion years, to stay just warm enough. Not forever, not without maintenance, but long enough for everything that has ever mattered to happen. That is what the cold makes visible in the end. Not its own emptiness, but the strangeness of warmth. The fact that it exists at all. The fact that it persisted long enough for something to notice. The universe does not tend toward warmth, and yet, here you are. Make of that what you will, in whatever warm place you have settled tonight. The stars are burning in the cold, as they always have, and the cold is patient, as it always will be.